Okay, in this numerical example, the figure 2.24, which is this figure here, show a uniform bar pivoted about point O. So it's a pivot point here, about point O with springs of equal stiffness. So this is K and K. At each end, the bar is horizontal in the equilibrium position with spring forces P1 and P2. So in equilibrium position, we have a spring force P1 and P2. Now determine the equation of motion and its natural frequency. So you need to calculate the equation of motion. And natural frequency, which is omega n. So you need to calculate these two things in this case. Okay, so now first in the equilibrium position, so if you consider this in the equilibrium position without giving any vibration here, so in equilibrium position, because there will be uh, some force here, which is P1, and there is a force here which is P2 here, and the center of gravity is here, so the mg will be in this direction here. So this is the free body diagram in this case here. Okay, so now if you again consider the summation of all the forces, all the moments from point O, which is this point here. This was our point of the pivot point here. And again, we know that the distance from O to the CG is C. And again, we know that this distance is A and this distance is B. So if you consider the summation of all the moments about O equal to 0, because in equilibrium position there is no acceleration, so it will be just equal to 0. And if we, for example, take the counterclockwise, the clockwise is positive, or the counterclockwise is positive. We are taking the clockwise is positive, for example. So it will be P1 times A. So P1 is the force and A is the moment arm of A. And then the weight is mg, and its moment arm is C, and then the minus, because the P2 is in the opposite direction. So it will be P2 times B equal to 0. So this is the equation at equilibrium position here. Or you can say that P1A plus mgc minus P2B equals 0 at equilibrium position. Now, if you give this system uh, some displacement from its equilibrium position, so it will start to vibrate. And now you want to draw another free body diagram at that position. So for example, if you consider that this was our equilibrium position, and now if you uh, just give it a small displacement, so this will be the new position of the bar. So this was the initial position, and this is the new position. If you give it a deflection here, angular displacement here, so now in this case uh, you will have a spring force. So obviously the forces that we have, so one is the P1, and now because you are moving the spring in the upward direction, so there will be uh, a spring force in the downward direction. So and This is obviously kx, and x is obviously the deflection at this location. And similarly, here you have P2, and because the body is moving downward, so the spring force will be in this direction. So you can call it maybe x1 and call it kx2, because the spring constant is the same. Okay, so this is the new free body diagram, and the mass is here, mg. So this is the and the distance from here to here is a, and here is b, and here is c. Okay, so now we want to write the equation of this system here, but first we will represent this x1 in term of a and theta. So here this x1 is just equal to a sine theta, which so if the angle is small, so we can say that it is a theta, and x2 is b sine theta, which become equal to b theta. So this spring force here become equal to k a theta, and this spring force here become k b theta. So these are the forces in term of theta, because the angle is very small, so we can represent sine by sine theta by theta here. Okay, so if we just again use the same equation here, summation of all the moments now equal to I not theta double dot here. So, and in this case, you can now you will have to take this one is positive, because this is our angular direction. So we will take theta double dot in this direction here. So if we take this is our positive, so P1 is positive, and this K A theta will produce a negative moment here. So to write the equation of motion, so it will be so P1 times A and minus K A theta times A, and now mg. So it will be positive, so plus mg, because it's in the direction of the torque here, into c here, and then you have this force here, so which is again again in the opposite direction. So P2 B, and then you have minus KB theta into B here, and equal to I naught theta double dot here. This is the equation of motion here. And now if you have noticed one thing, that we just multiplying this with A, you have to multiply with A cos theta. So in this case, A cos theta is equal to A, because again angle is very very small. So if angle is small, so then you can multiply with A cos theta, which become equal to A. So we are just using A here. So now we have this equation here. So in this equation, you can see that this P1A plus mgc minus P2B is equal to 0. This means that this term and this term and this term will will just equal to 0 because P1A plus mgc minus P2B is equal to 0. So if you just take these three terms, this is equal to 0. We can remove this from this equation here. So what will left in the equation is minus uh, ka square uh, b square and then theta equal to I naught theta double dot. Or you can simplify this equation by theta double dot plus ka square plus kb square I naught theta equals 0. Uh, or you can just compare this equation with this equation here. If you consider this equation 1 and this equation 2, and you say that comparing 1 and 2, so omega n will become equal to k a square plus b square I naught under the root. So this is our omega n in this case here.